Hello students, good morning. Now in this lecture we will discuss about the Savrat law. Savrat law. Here a arbitrarily shaped wire is shown. I is the current passing through this wire. Now by using the Savrat law, we have to find the magnetic field at a point. Magnetic field at a point at a distance r from the wire. This wire is not straight. This is arbitrarily shaped wire. Now, the magnetic field produced around this wire due to the current carrying or current passing through this wire. I is the current flowing through this wire, and therefore due to this current the magnetic field will be produced around the wire, and we have to find that magnetic field produced around this wire due to a current at point P. Now, suppose this is the direction of current. I is the current and this is the direction of current. By using the right hand thumb rule, we can find the direction of magnetic field at this point. This is the right hand thumb rule. We have already discussed about this right hand thumb rule. When a current carrying conductor is held in our right hand, that the thumb is pointed in the direction of current. If thumb is pointed in the direction of current, then these fingers curled around this conductor will indicate the direction of magnetic field. And when we taken this in this side, then these fingers are in inward direction at this point. At this point P, the fingers are inward direction into the plane of paper. Therefore, the direction of magnetic field at the point is inward direction or into the plane of paper, and here a symbol of magnetic field is shown. This symbol means that the direction of magnetic field is into the plane of paper. Now, consider a wire of infinite length L. Consider a small element of this wire of length dl. We have taken a small element of this wire, and length of this small element is dl. L is the total length of wire, then small element is considered here. Therefore, dl is the small element of this wire, and P is a point from this small element at distance r. This is the direction of element vector. This is the direction of this element vector. Therefore, we can say that theta is the angle between the direction of element vector carrying current I and the vector r. The vector r. Here, vector r is shown here. That is the position of this point. Therefore, theta is angle between element vector dl and the r, that is the distance from the element vector to that point where we have to find the magnetic field. So here the current in differential length element dl produces a differential magnetic field dB at point P. We have to find out total wire, but at start or initially we have to consider only a small length, but the current in differential length, then we will take again number of small elements of this wire and then adding this all the magnetic fields due to the differential length of this wire, and we can find out the total magnetic field at this point P due to the total current flowing in this wire. Therefore, the current in differential length element dl produces differential magnetic field dB at point P at a distance r from the wire. Therefore, when we have to take the total magnetic field, we have to take initially the magnetic field due to a small element, and by integrating this equation we can find out the total magnetic field. Now this magnetic field produced due to the current in the small element dl is directly proportional to this dB is the magnetic field produced at point P due to the current flowing in the small element dl of wire, and this is directly proportional to current flowing in the wire. As the current increases, the magnetic field also increases. Therefore, magnetic field is directly proportional to current. Then it is directly proportional to length of small element. As the length of small element increases, then magnetic field also increases at this point. And then it is also depend upon this sign of angle theta. Sign of angle theta between this element vector and this distance vector. Therefore, we can write here dB is directly proportional to I dl sin theta. As the distance of point P increases, if we take point this at this point, if we take point P as here, then magnetic field at this point will be decreases because distance from the wire increases. As the distance increases, magnetic field decreases. It is inversely proportional. Therefore, or it is inversely proportional to square of distance. Therefore, we can write here dB is inversely proportional to square of distance. Therefore, dB can be written as dB is equal to mu 0 upon 4 pi into I dl sin theta upon r square, where dB is the magnetic field due to a current passing through a small element dl. Mu 0 upon 4 pi is the proportionality constant. This mu 0 upon 4 pi is proportionally constant, and the value of mu 0 upon 4 pi is equal to 10 raised to minus 7 Tesla into meter per ampere. Tesla into meter per ampere. Here a new symbol we can see, that is the mu 0, and this mu 0 is known as the permeability of free space. We will discuss about this permeability of free space. Then here I is the current flowing through this conductor, dl is the small element of length dl, and theta is the angle between small element, direction of small element or vector element, and the vector displacement. This mu0 also known as permeability of the free space, and r is the distance of a point P from the small element dl. Now, if we want to take a total magnetic field, then we have to take the integration of this equation. By integrating of this equation, we can find out the total magnetic field at point P due to a current flowing through this wire. Now, in the vector form, if you want to write a vector form of this equation, then we can write here a vector dB is equal to magnetic field is a vector quantity, therefore vector dB is equal to mu0 upon 4 pi I dl. We have to take a cross product. We have to take a cross product of two vectors. Here theta is the angle between r and dl. Therefore, we have to take a cross product of dl and r. Therefore, here is a no quantity r. Therefore, we can take r here. This vector dl cross r, and here we can take as the r cube, because here we have taken one extra r which is not here in this equation. Here is taken r, and therefore we can take here r cube instead of r square, and this is the vector form of the magnetic field at point P. Magnetic field at point P. Now we will discuss about the permeability of the free space, that is about the mu. Here Bdt of free space, that is mu0. Permeability of free space mu0. In electrostatic, we have already discussed about the epsilon naught. Here epsilon naught is the permittivity of free space in electrostatic. This mu naught is also same quantity as that of epsilon naught. That is, epsilon naught is the permittivity of free space, and mu naught is the permeability of the free space. Permeability of free space, it means when we or permeability of any material, that is we take as mu is the permeability of material, mu naught is the permeability of free space. Now permeability of material means when we take a material in an magnetic field, when we put a material in an magnetic field, then how much this material responds to the magnetic field, how much this material responds to the magnetic field. That is, magnetic permeability is the term permeability can be said as it is the number of magnetic line of force that are passing through a given substance when it is kept in a magnetic field. That is, permeability of a material means the number of magnetic lines of force passing through that material when this material is kept in a magnetic field. We know that there are three types of materials as when we think about the magnetic field: diamagnetic material, paramagnetic material and ferromagnetic material. Here, the diamagnetic material does not respond to the magnetic field, or they opposes the magnetic lines of force to pass through them, where paramagnetic materials respond to the magnetic field, or they allows the magnetic field to pass through them. And the ferromagnetic materials are the materials which respond strongly, or which attracts the magnetic lines of force strongly when this material placed in magnetic field. Therefore, we can say that the permeability means the response of magnetic field, or response of material to the magnetic field to allow to pass through them. Therefore, permeability of diamagnetic material is very low, or it is about the negative, and permeability of paramagnetic material is more, and whereas the ferromagnetic material, it is permeability of ferromagnetic material is maximum. If we consider about the superconductors, that is, for superconductor, the susceptibility is -1. For superconductor, susceptibility is -1. That is, we can say that the magnetic permeability or permeability of superconductor will equal to 0. Permeability of superconductor will be equal to 0. And when we take the soft iron, the susceptibility of soft iron, that is, susceptibility for the soft iron is greater than 1000. Therefore, the permeability of soft iron also the maximum. Therefore, we also use the soft iron for the strong magnetic field to pass the magnetic field through it. And this is the value of the permeability of free space. Mu naught is the permeability of the free space, and the value of mu naught is equal to, here mu naught upon 4 pi is equal to 10 raised to -7. Therefore, mu naught will be equal to 4 pi into 10 raised to -7 Tesla into meter per ampere. Tesla is the magnitude of magnetic field. M is the unit of length, and here A means the ampere. Therefore, the mu naught, that is permeability of free space, is equal to 4 pi into 10 raised to -7 Tesla meter per ampere. Now we will discuss about, or we can also write here, we can discuss about the current in the stretched long wire. Okay. Now we will discuss the current in a straight wire by using the equation derived from the Savrat law. Here, this is a straight conductor. I is the current passing through this wire, and we have to find out the magnetic field at point P, which is at distance, or we can say a perpendicular distance r from this wire. This is a perpendicular distance of point P from this wire is r, and we have to find out initially a magnetic field due to a small element of length dl, and by integrating this all the magnetic fields dB for differential length dl, then we can get a total magnetic field at point P due to a current passing through this conductor. Now I is the current which is shown here in this direction. Therefore, we can say when we take a small length dl at this point on the wire, then this is the direction of length vector in the direction of current. We have to take the direction of length vector, that is dl, in the direction of current, or we can say the direction of element vector, and therefore this r is the distance of point P from the small element. This is the direction of element vector, and this is the direction of distance of point P from the small element, and this is the theta between the dl and the r. Angle theta between the dl and r is this angle. Now we have to find the direction of magnetic field at this point. Again, considering a right hand thumb rule, then when we take a conductor in right hand, this is the direction of current. The thumb is pointed in the direction of current. Then the fingers at this point are inward direction here. Therefore, magnetic field at the point P will be inward direction. That is, magnetic field can be say that magnetic field is equal to, it is the dl cross r. That is, we can say the direction of magnetic field. The direction of magnetic field is dl cross r. Therefore, and the direction of magnetic field is into the plane of paper. Therefore, we can say here the symbol of direction of magnetic field which is into the plane of paper. Now, consider, or we can, using the Savrat law, we can write the equation of magnetic field dB is equal to I to dl, or in magnetic form we can write here I dl sin theta upon r square into mu naught upon 4 pi. dB is equal to mu naught upon 4 pi into upon r square. This is the magnitude of magnetic field. By using this equation, we have to find the magnetic field due to the current in a straight wire. Now, at first, we will consider a upper part of the wire, the upper half part of the wire. Therefore, when we take a magnitude of magnetic field at point P by the current length element in the upper half of the wire, and then second we will take the magnetic field at P by a current length element in the lower half of the wire. Therefore, we can take by integrating this above equation, then we will get the integration limit can be taken as this dB is equal to integration is taken as in limit 0 to infinity, then mu 0 upon 4 pi I dn sin theta upon r square. We can say the equation A or equate for point A. Then dB in the lower part, that is given by dB is equal to integration in limit 0 to infinity mu 0 upon 4 pi I dn sin theta upon r square. Say equation B. When we have to find the total magnetic field of this, then we can take, or here also we can take the integration. Then total magnetic field will be get by adding this equation A and B. Therefore, the total magnetic field B will be equal to integration 0 to infinity to dB. Adding equation A and B. By adding equation A and B, we can find out the total magnetic field at point P. In this first point, we have find the magnetic field at point P by the all current length element in the upper half of the wire, and here current length element in the lower half of the wire. We have to take two parts of the wire, upper part and lower part. This is the magnetic field for the upper part, this is the magnetic field for the lower part, and therefore total magnetic field will be equal to B, will equal to integration of dB. Now, this magnetic field will be equal to dB, and this will be equal to dB is equal to mu naught upon 4 pi I dn sin theta upon r square. We can take mu naught upon 4 pi outside the integration. Then we will get I dl sin theta upon r square. The total magnetic field B is equal to mu naught upon 4 pi into 2 integration of ideal sin theta upon r square. This 2 will be cancelled here. Therefore, mu naught upon 4 pi integration of 0 to infinity ideal sin theta upon r square. We can take this I out of the integration because this is also the constant term. I is the current passing through this conductor and it will be same at every point. Therefore, it is not necessary to take inside the integration. Therefore, now we have to take the integration of this dl sin theta upon r square. By considering this figure, this is the perpendicular distance r from the point P up to wire. Therefore, from this figure, this will be 90-degree angle. Therefore, we can write here by the Pythagoras theorem, r square is equal to L square plus r square, where L is the length of wire. R square is equal to L square plus r square. Therefore, r is equal to under root of L square plus r square. R square is equal to under root of L square plus r square. Now again, when we consider this angle theta, then this angle will be equal to, total angle is 180 degree or we can say pi. Therefore, this angle will be equal to pi minus theta. Therefore, we can say the sin theta is equal to, we know that the formula, mathematical formula, sin theta is equal to sin of pi minus theta. By considering this triangle, pi minus theta is this angle. Therefore, sin of pi minus theta will be equal to r divided by small r. Therefore, capital R divided by small r. Therefore, we can write here sin theta is equal to r. Instead of small r, we can write here under root of L square upon r square. Capital R upon under root of L square plus r square. Therefore, instead of sin theta, we can write this in equation. Here we can say the equation 1. Putting the value of sin theta in equation 1, then we will get the magnetic field B is equal to this. Here is not 4. This 4 is cancelled here. Therefore, mu 0 upon I into 2 pi. Here B is equal to mu 0 I upon 2 pi integration of 0 to infinity. Then dl r upon sin theta. Instead of sin theta, we can write here r upon under root of L square plus r square into dl upon this r square. This r square is equal to L square plus r square. Therefore, this will be L square plus R square. Then these are taking outside the integration. Mu 0 R upon 2 pi into R. We can say here dl upon under root of L square plus R square. It means it is the raised to 1/2 into L square plus R square. We can write here R adding the power of these two brackets, we will get L square plus R square raised to 3/2. By using the mathematical formula of integration of 1/L square plus R square raised to 3/2 with respect to dl, then we will get V is equal to mu naught I 2 pi R. The integration of this equation will be equal to 1/R square. By using the mathematical formula, we can solve this term, or we can take the integration of this term. We will get 1/R square. Therefore, by cancelling this R, we will get upon 2 pi R. This is the magnetic field at point P due to a straight wire carrying current I, where B is the total magnetic field, mu naught is the permeability of free space, I is the current passing through the wire, then this R, capital R, is the perpendicular distance of point P from the wire. This is the equation, required equation for the current in a straight wire. Now, if we want to find the magnetic field at point P due to the semi-infinite straight wire, magnetic field at point P due to semi-infinite wire, then we can write here mu naught I upon 4 pi R. This is the magnetic field for total whole wire or whole infinite long wire. For the semi-infinite wire, dividing this equation by half, 2, dividing equation by 2, then we will get mu naught I upon 4 pi R. B is equal to mu naught I upon 4 pi R. Okay.